On Black Friday 2021, 2 engineering teams hit AWS Lambda limits within the same hour. The first team received a monitoring alert at 8 a.m. Lambda was throttling. Requests were slowing, not stopping. They had time to request an emergency limit increase, adjust their application's retry logic, and keep the service alive. Their checkout recommendation system degraded for 20 minutes. Orders processed throughout. The second team's payment confirmation service stopped. No monitoring alert had come first. No error rate had climbed gradually before the failure. Lambda had hit a different limit entirely, one that does not throttle, it refuses. Orders failed for 9 minutes before the team identified the cause. Same cloud platform. Same AWS service. One limit warns, the other does not. The assumption most people make, after learning that cloud services have limits, is that limits behave consistently. When something reaches its ceiling, it slows down, signals, gives you something to respond to. This assumption is understandable. It is also wrong, and treating it as true is one of the more expensive mistakes in cloud operations. When a limit gives you warning, when the service throttles rather than refuses, when error rates climb gradually rather than spiking immediately, you have options. You can reduce load, implement backoff, request an increase, or prepare stakeholders before customers notice. The limit has made the situation manageable. When a limit refuses rather than throttles, those options are not available. The service is working or it is not, and the time between those two states is measured in seconds, not minutes. This difference is not accidental. It reflects a structural distinction in how cloud limits are designed, one that determines not whether a problem is solvable, but how it is solvable, and by whom, and in what time frame. Understanding the distinction before a production incident is the only time it is useful to know it. A gas furnace has 2 separate mechanisms that can both stop it from running. The first is the thermostat. You set it to a target temperature. When the room reaches that temperature, the thermostat signals the furnace to stop. The room cools, the furnace starts again. The set point is a limit, but an adjustable one. You can change it whenever you want. If you decide the room should be warmer, you raise the set point, and the furnace responds to the new value. The thermostat is designed to be changed by the person using the system. The second mechanism is the high limit switch. This is a safety device mounted inside the furnace that monitors the temperature of the air in the heat exchanger. If that temperature exceeds a fixed threshold, typically between 80 and 90 degrees Celsius, the switch cuts power to the burner immediately. It does not wait for the room temperature to respond. It does not send a warning first. It does not respond to the thermostat setting. Its job is to prevent the heat exchanger from overheating and cracking. Once it trips, the furnace cannot restart until the unit cools and someone physically resets the switch. 2 stopping mechanisms. 1, designed to be adjusted by the user and to regulate behavior within a range. 1 designed to be absolute, protecting the underlying hardware, and resolved through intervention rather than configuration. Cloud limits work on the same principle, and the analogy holds up to a clear point worth naming. A thermostat does not alert you before the room reaches temperature. Many cloud soft limits can be monitored in advance, their headroom tracked, alerts configured, which is part of what makes them more manageable in practice. But the structural distinction is the same. One limit can be moved by the user, the other cannot be moved at all. A soft limit is a cloud resource ceiling that can be increased through a request to the provider. When an application reaches a soft limit, the cloud service does not cut off access immediately. It throttles, it slows the rate of requests, or returns an error code that signals the client to back off and retry, or queues excess load while rejecting new requests above the threshold. The behavior is designed to be survivable. An application that handles throttling correctly, that implements exponential backoff, that retries at a reduced rate, that fails individual requests gracefully while the overall system continues running, can operate at or near a soft limit for extended periods while a limit increase is being processed. Soft limits are also visible before they are hit. Most cloud monitoring systems can track the distance between current usage and a soft limit threshold. A team that has configured this monitoring knows when an account is at 60% of its concurrent limit, at 80%, at 90%. The limit becomes the object of a deliberate, planned response rather than a crisis. AWS Lambda's concurrent execution limit is a well-documented example of a soft limit in practice. New accounts in a region start with a default of 1,000 simultaneous function executions. This number can be increased through a support request to values in the tens of thousands. When an application hits the concurrent execution limit, Lambda returns a throttling exception. The function did not run, but the request can be retried. The limit is visible in AWS's Service Quotas console. Its headroom can be monitored through CloudWatch, and the increase process is documented and expected. A hard limit is a cloud resource ceiling that cannot be increased through any request. It represents either a physical constraint in the underlying infrastructure or an architectural boundary in how the service is designed. When an application reaches a hard limit, the cloud service refuses. Not throttles, refuses. Requests that exceed the ceiling return an error, with no retry path that will succeed, no backoff strategy that will resolve the problem, and no support ticket that will raise the ceiling. The only path forward is changing how the application uses the resource, redistributing load, moving to a different service type, or redesigning the architecture that created the demand. Lambda's burst limit sits alongside the concurrent execution limit as a parallel, harder constraint. The burst limit governs how quickly the concurrent execution count can increase within a short time period. It reflects the physical capacity the regional infrastructure can bring online in a short burst. At the burst limit, Lambda does not throttle. It refuses the invocation with a different error from the soft limit version. No support request will raise the burst limit. The application must spread its traffic differently, or reduce its peak demand, or distribute load across regions, each of which is an architectural decision, not an operational one. The practical consequence of this distinction is that the same error message, a function that fails to execute, an API call that returns an error, can indicate two completely different situations. One is resolved by a limit increase and a configuration adjustment. The other requires an architectural change. Diagnosing which situation you are in before deciding on a response is not a detail, it is the whole problem. The two categories are not always clearly labeled in provider documentation. Most major cloud platforms distinguish between adjustable and non-adjustable limits somewhere in their documentation, but a large deployment may involve dozens of services, each with its own set of limits, each marked differently in different parts of the provider's console. Teams that have not read the relevant documentation before they need it will discover which category applies at the worst possible moment. There is a further complication. Some limits are described as soft. They can be increased, but have a de facto ceiling on how far they can be raised. A concurrent execution limit that can be increased from 1,000 to 10,000 is a soft limit. An attempt to increase it beyond the regional capacity available will be declined, or will require infrastructure changes on the provider's side that take time. At that point, the soft limit has become a hard one in practice, through the physics of shared infrastructure rather than through policy. And soft limits do not automatically protect you. Throttling errors at a soft limit cause cascading failures in applications that have not implemented retry logic. A soft limit saves you only if the application layer is designed to respond to the signals it sends. An application that treats a throttling error the same as a permanent failure will behave, at a soft limit, identically to how it behaves at a hard one. The limit type determines what is possible. The application determines whether what is possible is actually achieved. The operational answer to this uncertainty is documentation before the event. Before a service goes to production, the limits that apply to it, adjustable and absolute, should be identified, their current values recorded, and monitoring configured to track headroom. This is a low-priority task during the pressure of building a new system. It becomes the highest priority task the moment the system fails under load. The two teams on Black Friday 2021 received the same error. Lambda was refusing to process requests. The error code was similar. The symptom, failed function executions, was identical. The first team raised a limit and adjusted their retry logic. They were running again within the hour. The second team had hit a limit that could not be raised. They redesigned their load distribution across regions. They were running again by the following morning. The first question to ask when a cloud limit is hit is not how to increase it. It is whether increasing it is possible at all. That answer determines the timeline, the recovery path, and who needs to be in the room. Soft limits and hard limits are not 2 degrees of the same problem. They are 2 different problems that announce themselves with the same error message.